All right. Anybody have any questions, homework questions or anything from the weekend? Let's just finish the example we were doing last time. So we had a pin joint here, and we had this funny shaped object. Like this. The total length is 2 meters. Half of it is this part and half is this part. And then it's 1 meter tall. And we've been working on centroid. So the first part of this problem was figuring out where the centroid of this was, so you knew where the weight force is applied. And we figured out that the centroid is over here, where this distance is 0.2 repeating, and this distance, I drew that a little higher than it should be, but it is above the midline, and that's 0.5 repeating. Okay, so now we're going to use that in a rigid body problem. So I'm going to draw a free body diagram. At the pin joint, no translations are allowed, well, this is in 2D, so there's only one type of rotation. It can rotate freely about that pin joint, so this is just going to be, I'll call it RA, a force vector. And then we have the weight force. This thing, I didn't look. Do you remember what the mass? What? 10? Okay, so 10 times 9.81. And then we have the roller here that's perpendicular to the surface toward the chosen body, so I'll call that RB. And so now I'll go rho, force, moment. And I'll put the about point up here. It doesn't matter where you put it. Another good option would have been to put the about point where I put the origin in calculating the centroid. Remember, if you put your origin at the about point that you use, the row vectors are all just the coordinates of the points where the forces apply. So that can sometimes simplify things. Okay, I don't know. I'm putting it up here. So first we have this force RA. From where the origin was, which is this, that row vector is going to be -1 for x, +1 for y. Force vector is R, A, X, R, A, Y. And so the cross product is -R, A, Y minus R, A, X. And then the weight force. Well, we have the location of that weight force in terms of this coordinate system. The row vector from the weight force to this point A that we're from the what we want for rho is from the about point to where that force is applied. So that's going to be positive 1 plus 0.2 repeating. So 1.2 repeating. And then negative, so yeah, 0.4, is that 4 repeating? 0.4 repeating?
I think so.
I think so too.
0.999 repeating, right?
Yeah, that's right. So negative 0.4 repeating. The weight force is, oh, and one thing too. Okay, so I just spent 12 seconds, thinking about what that y component of that row vector is. But notice that the line of action for this force is this. So it doesn't matter. Okay, so I'm going to actually make this 0. Doesn't matter. So 0, negative 98.1. Can someone multiply 1.2 repeating to negative 98.1 for me?
Are you okay?
I think it's going to be
119.9.
That's not what I thought it was going to be. Negative 119.9.
I got 117.7.
Ooh, that's what I thought it was going to be. 0.7 repeating, probably.
Yeah, it's if you do it to one digit to 1.2, it's negative 117.7.
Okay.
But if you do it to more, it's 119.89, so on.
119.89.
Yeah.
0.90. 119. Okay, that's what you said.
So if you do more digits.
Okay. And then the last one is the force RB. And that row vector is going to be 2 for the x component and negative 1 for the y component. The force is 0 RB. You get 2 RB for that. Okay, so up until now, we've made our life harder by choosing the about point at a different spot than we had our origin for the centroid. But from this point on, it's going to make it a little simpler. We can probably do it without using reduced row echelon form and stuff. Yes?
I'm a bit confused for the row vector for RA. Shouldn't it be 0, 0?
Yes, I went to the, thank you.
Yeah.
Yes. Yes, you are right. That is the whole reason that you put it, that's the whole reason that you put the about point at one of those forces. Okay, so that's 0. Thank you. Now the force equation, Newton's second law, says RAX, RAY plus 0, negative 98.1 plus 0 RB is equal to zeros. And the moment equation says 2RB minus 119.9 is equal to 0. So RB is equal to 59.95. And so RA then is equal to 0 for X. And for Y, can someone subtract that? So 98.1 minus 59.95. 38.15. Okay, so if you look at a free body diagram, you have the weight force here of 98.1. You have at A a vertical force of 38.15. Here you have a vertical force of 59.95. Would these reactions be different if this, instead of being this funny shape, was just a big rectangle that had the same mass?
Yes.
It would.
If it shifts the center mass.
Yes, that's right. So if this was just a rectangle, what you would get is that vertical force at A and that vertical force at B would be the same. Okay? But since our center of mass is shifted to the right, the support at the right has to support a bigger fraction of that total force. Okay?
Can you talk to, so obviously we put 0 as the y component of the weight force.
Yeah. Of the force or the row vector?
The row vector.
Okay.
Was that an equipolant?
Yes, that was an equipolant system because you can always move any force anywhere you want along its line of action. So this force's line of action is this blue dotted line. And you can, without changing the math, as long as you're treating the thing as a rigid body for that part of the calculation, you can move this anywhere you want along that line and it doesn't come into the math.
So even if it's a force that has 2 components, that would just mean its line of action is forward.
Right, exactly, yep.
The cosine sign of that.
What?
We would act in the cosine sign if it was like that at a.
Well, it would, yeah, I mean, if that force was this, then it gets a little, and if your coordinate system isn't aligned in some way with this, then it's a little harder to take advantage. It's probably not worth the effort of figuring out where you can move it. But yeah, you can always, if you're treating the thing as a rigid body, you can always move the force anywhere along its line of action.
Okay, so when you're solving, you can sometimes get an extra 0 you can move it
Yeah.
somewhere so that you get a 0.
That's right. And I mean, what if I wouldn't have put this as 0? You know, if I would have put it as positive 0.4 repeating, you know, but you can see when you take the cross product, it's this times this minus 0.4 repeating times 0, and that's why it doesn't matter.
So does working backwards, does it mean it's in, the movement would be equipolant if your cross product, if it wouldn't matter if you had it when you're doing the cross product?
Yes. Yep,
So how
that's
you
right.
can- If you do that, you can sort of check it when you're doing the cross
Yeah.
product.
And I suppose that's the way you would prove that it's an equipolant system, you know?
Okay.
Make a general thing at a general angle and you show that it doesn't come into the to the cross product.
So you can do that with RB as well if you wanted to.
Yes, exactly. Yep, exactly.
Do what with RB?
Move it along. So now I drew the line of action of RB. I could have written the y component as 0 for this, and you can see again that would go away because the line of action of RB is this.
Okay, so as a rule of thumb, like if you have it's acting vertically there,
Mhm.
you can just drop off the y.
Yeah, and if it's horizontal, you can drop off the x, and if it's not horizontal or vertical, it's probably not worth it. But you could deal with it along that line too. And remember, you don't have to. So your mind always wants to be like, you know, well, it has to be on the body, you know, like that's a common thing. So like you can't move it anywhere. Well, yes, because it's just a mathematical thing. So if you wanted to move it 50 miles off the body along the line of action for some reason, it doesn't change the math, you know. Okay, any other questions about that? So now we're going to use centroids for distributed loads. And distributed loads are forces of force spread out over an area or a distance. And so we'll see them in stuff like this. If you have a beam, you could see a distributed load that would look like this. And at the greatest point of this distributed load, it has a value of 2,000 newtons per meter or something like that. Okay. Really, all forces are distributed loads. So notice that first of all. There's no such thing as a point force. The sharpest knife blade that you could come up with still is going to touch the body over some distance, you know. But point loads often are good approximations, and they sure make things simpler to deal with. But every force, if you're really trying to be perfectly detailed about it, is spread out over some distance or some area. Okay, so the first thing I want to do is give you just a little bit of sort of intuitive, like something to help you wrap your head around what this means. Okay, so I want you to think of a distributed load in comparison to like the speed of a car or whatever moving along the highway. So think of the relationship between a distributed load and a point force. The same way you think of the relationship between instantaneous speed and distance traveled. And maybe instead of point force, change this to total applied force. Just to erase that, just use your electric eraser and it'll just erase it completely. Okay, so first of all, at a single instant, say your car is going 60 miles an hour, at a single instant, how much does that make your car travel? You know, I mean, you're used to thinking of it that way. It doesn't travel anywhere in an instant, you know. So an instantaneous speed doesn't travel any distance at a single instant. In an instant. And you can think about a distributed load the same way. Choose some point along that beam and ask yourself, what's the force that's applied? The answer is at any single point, the force is 0. Okay? So a distributed load doesn't apply a finite force, any finite force, at a single point. So how does a speed, something moving a speed travel a finite distance? Well, there has to be some time interval that there's a speed, okay? Like if you say, what's the distance traveled over 1 second, then okay, then you can integrate over that time and you do get a finite distance traveled. To travel a finite distance, you need a speed over a time interval. So the analogy with distributed load is to produce a finite force, a distributed load has to act over a spatial interval, to produce a finite force, a distributed load must act over an interval in space. Well, that's an interval, let's say, of distance, you know what I mean? And then third, so how can you think of, like, what does the distributed load mean? Well, what does the speed mean? It says that, so your speed is how far you would travel if that was the uniform speed you traveled for an entire unit of time, right? So 60 miles per hour means if you stayed at 60 miles per hour for a full hour, you'd go 60 miles, right? That's what a distributed load means too. Okay, so if you have a distributed load of 2,000 newtons per meter, it means if that was a uniform distributed load, which this isn't because you can see it's changing over distance, but if that was uniform over a full meter, it would apply a force of 2,000 newtons. Okay, so the instantaneous speed says if it were uniform over a unit of time, that's the distance you would travel. And a distributed load if it was uniform over a unit of distance, that would be the total force. Okay, another way you can think about it, you'd think this is the equation that we would use all the time. We're not going to use it that much, but you can think of it as the total distance is the integral of the speed with respect to time. the analogous thing for distributed load is that the total force is the integral of the distributed load over x. Okay. Or if it's a distributed load over area, which we're not going to use in this class, it would be dA, you know. Okay. So how do you do this? So the to use distributed loads, with Newton's laws, you first are going to replace the distributed load with a point force, but it has to be an equipolant system or you get different answers. So we're going to always replace the distributed load with an equipolant point force. And that point force always acts at the centroid of the distributed load shape. The magnitude, yes.
Does this only apply for a uniform load?
No.
Okay.
Yeah. So we'll start with the uniform load, and then we'll do a lot of triangular distributed loads. You could use any funky shape. You could use parabolic shape distributed loads or whatever, but the application of those isn't as obvious, you know. Okay, the magnitude of that point force well, I gave you that integral relationship, and integrals over a distance give you an area. So as you would imagine, the magnitude of that point force is the area of the distributed load shape. Okay, so let's do an example. So let's say we have a beam with a roller at one end. And let's say that the distributed load is 3,000 newtons per meter. This one is uniform. We'll ignore the weight of the beam. We'll say that this distributed load produces a force that sort of dwarfs the weight of that beam, so we'll just ignore it. Okay. And let's say that the length of this is 2 meters. And we want to calculate those reactions. Okay, well, a free body diagram has a point force over here, I'll call it RA, from the pin joint, and a force vector RB here. And then we have this distributed load. I'm going to start by drawing that again just as a distributed load. But before we do the calculation, we'll have to represent that as a point force. Okay, so the centroid of that shape and the area of that shape. So this is a rectangle, this shape. Rectangular distributed load. The width of this rectangle is 2 meters. And the height is 3,000 newtons per meter. Don't worry about drawing it to scale or whatever. Those are different units, so there's no way to really do that anyways. Well, the centroid is going to be right in the middle. So that's the location. And all of the distributed loads for now, for most of the class, that we're going to deal with are going to be vertical. They're going to be just acting straight down. And so notice that the point force is going to be straight down. And so all we care about is the X location of that centroid. The Y location really doesn't mean anything in this case. I mean, it's not really physically acting there. All that matters is the X. And then what about the area? So the area of this shape is 3,000 newtons per meter times 2 meters. And the units work out because the meters cancel and you get newtons. And so the total area is 6,000 newtons. So now I'm going to redraw this free body diagram. We have a weight force, or a distributed load force, acting down right at the middle, because that's where the centroid was, with a total force of 6,000. And then we have these forces. And now you can do that calculation. I'll show you a quicker way to do this for beams pretty soon, but remember that we're just doing a rigid body calculation, so you always can write out the whole table and do it like this. So if my about point is here, RA has a row vector of 0. The force is RAX, RAY. Cross product is 0. Then the distributed load, the 6,000 Newton force. This has a row vector of 1, 0. Force vector is 0, negative 6,000. So the cross product is negative 6,000. And then RB has a row vector of 2, 0. Force is 0, RB. And so the cross product is 2, RB. And if you go through Newton's laws on that, because of the symmetry of all this, it's just going to come out to say that RA is equal to 0, 3,000. And RB is equal to 3,000. Okay, so the key step is going from that distributed load to the equipolant point load. So now let's do one where we have a cantilever beam. So let's say that it connects to the wall on the left. And let's say that the length is 2 meters again. And the distributed load has a triangular shape. With a maximum of 10,000 newtons per meter. And we want to know what are the reaction loads at the wall. Okay, well, let's first think about the centroid location and the area. So if this is the distributed load, and it has a base of 2 meters and a height of 10,000 meters, 10,000 newtons per meter. The centroid of this shape is a third of that 2 meters from this side. Okay, so this is going to be 0.6 repeating meters. And that means that the distance to the centroid from this side is 1.3 repeating meters. And like I said, we could calculate that vertical centroid, but it doesn't matter for anything. It doesn't mean anything. Okay. And the area of this shape is base times height over 2. So that's just 10,000. And now I'll draw the free body diagram. I just did this first so I could jump right to a free body diagram with that point force instead of first doing the distributed load and then going to the point force. But okay, so here's the beam. What loads are acting at the wall? Yeah, it's not allowed to rotate and it's not allowed to translate. This is a fixed joint, so we have this reaction force R, and then I'll call this couple MR, like reaction moment. And then 2/3 of the way along this length, we have the equipolant point force with a magnitude of 10,000 newtons. This area shouldn't have a per meter in it. So now you can fill out rho, force, moment. For the force R, let's put our about point over here. So row vector is 0. The force vector is r, x, r, y. Cross product is 0. Then for the couple MR, we don't care about these two things. Those aren't relevant for couples. And so we just have the couple of the moment of MR. And then last, we have that 10,000 Newton force. The row vector, from the about point to where that force is applied, has an x value of 1.3 repeating. We got that from the centroid of the triangle. And then it doesn't matter what you choose for y, it's not going to come up. The force vector is 0, negative 10,000. And so the cross product is negative 13,333. So Newton's second law says Rx, Ry, plus 0, negative 10,000 is equal to zeros. And right away, this tells us that this force vector is equal to 0, positive 10,000. And then the moment equation says MR minus 13,333 is equal to 0. So MR is equal to positive 13,333. And what are the units for this? Newton meters. It's a moment. Yep. Okay, does it make sense that, so it makes sense physically that R has to be up to balance that downward force of 10,000, right? Does it make sense that we got a positive moment for the couple applied at the wall? Yeah, I mean, if you think of it as that about point over there on the left, think of it as a hinge. That 10,000 Newton force is making it rotate clockwise. That would be a negative moment. And that means that the couple applied at the wall, the balance, that has to be positive.
So does the material, with the way materials work, I would assume it would have to, the torque it can take is less than the translation.
The downward force?
Like materials in general, do they take less torque force than they would translational force?
Yeah, like how likely is it to break based on that? Yeah. So that question has to do with stresses and strains in the material, and so the question is the stress due to a bending moment bigger than the stress due to a shear force? And so
I know you don't need to get
yeah,
inside.
it won't be. Yeah, it won't take very long. But like the stress due to bending comes from this formula, where this I has something to do with the shape of the material, and the stress due to shear force has to do with, so the shear force times this shape factor over I times B, and these things both have to do with the shape. Hold on. So these are also determined by the shape. And so I guess the answer is, the sort of mathematical answer is, it depends on the shape of the material. In practice, there are a lot of cases where you're more likely to break like normal engineering shapes, normal engineering objects through bending than you are through shear force.
Okay.
Yeah. Any other questions?
When you find the centroid of an object with removed area, do you just subtract that in your sum equation?
When you find, oh,
So if you're removing area,
yeah,
you just subtract it.
you subtract it. That's right. That's what you do. So make sure that, so the formula says 1 over the total area times the sum of this. Okay, so there's the sum formula. For calculating a total, remember to use the actual area of the true shape. Okay, so you have to subtract the removed shape to get the total area, first of all. And then you also have to think of it as a negative area, you know, when you're using the sum formula. So for the removed shape, this area would be negative, and so you subtract that term. So you kind of subtract twice, you know. Any other questions? Okay. Well, I'm going to, for the assignment today, give you some sort of simple versions of problems like this. And yeah, see you Wednesday. Really, I'll see you in 10 minutes.